So the job again today is to take the ideas of linear equations that we developed yesterday. In other words, we saw what y equals mx plus b can look like in a scientific context. We know that y and x are our independent and dependent variables, and that m and b are the parameters, m being the slope parameter, b being the intercept parameter. And what we looked at yesterday was how to provide a context specifically for the slope, how to provide a context and how to get units for what the slope parameter of a linear equation actually tells you. And then we also talked about the intercept. We looked at some examples of when this data was exactly linear. We looked at a couple examples of when it wasn't exactly linear, but you could use a line of best fit using Excel or using some other software to come up with a linear equation that basically fits a set of data. But what we want to do with this today is apply the same kind of thinking to data that is not necessarily linear. So I want to start by looking at this problem. So suppose we're astronauts standing on the moon and we're going to drop an object on the moon. Well, objects on the moon fall a lot like objects on Earth would fall, under the acceleration of a uniform gravity. And we have a model equation up here that describes the relationship between height and time, which is exactly the same model equation as you would have for height versus time on the surface of the Earth. The only difference is that the acceleration due to gravity on the moon is a different constant, a different g, if you will, than the acceleration due to gravity on Earth. So suppose we're on the moon, we drop an object, I don't know, a golf ball or something, and we take some measurements of the relationship between height and time. So we have this set of data points. So the first thing I want to know is, does this data fit a linear equation model? In other words, is this data linear? First of all, what's your suspicion? Do you think this data is going to be linear or not?
No.
Probably not. How come?
T has an exponent.
Yeah, take a look at the model equation. If this data really does fit this particular model equation, well, this model equation is not linear in the variables t and h. It has a t squared in it. So probably this is not going to fit a linear equation. At least not a linear equation if we're thinking of, what do we think of our dependent variable as being here? What's playing the role of our y, do you think?
H.
Yeah. So if we try to fit this to a linear equation where h is the dependent variable, and that would make t the independent variable, let's just verify that that is not, in fact, going to happen. So what I'm going to do is just take these data points and let's plot them on a set of axes and see whether or not they fit a straight line. So I've placed the first two data points on this graph already. And notice, as soon as we put two data points on a graph, immediately, what do we definitely get? A straight line, right? Two data points will always have one and only one line, as long as they're different points passing through them. But when I go to put my third data point on here, it's about where my mouse cursor is. So what does that immediately tell us? If my third data point is down here, then it probably means this is not actually a linear model, right? At least that third data point is far enough away from the line that the other two determine that probably, if we were to find a model that better matches this data, that model would have to somehow curve downward. It can't just be a straight line. In fact, given that this is curving downward away from that straight line, calculus people, what is this kind of curve called? Well, probably a parabola. And the presence of the t squared in our model equation is a hint to that. But even if we don't know that it's a parabola, we at least know, because it's bending downward, we can say, in calculus terms, that this graph is probably going to be concave down if we were to sketch it as honestly as we could. So a linear model is probably not most appropriate. Let's place that data point and then see what we're up against. So when I place those three data points, I still have a line of best fit that goes through those three data points. It's just that the correlation coefficient of that line of best fit is now, well, actually it's still pretty decent. R squared of 0.986 is not the worst thing in the world. But maybe we can do better. particularly since we have this model equation, h equals minus g over 2 times t squared plus h naught, where h naught is the initial height from which this object was dropped, h is the height at time t, and g is the acceleration due to gravity. We have this model equation that is not a linear equation. So can we use the same ideas behind linear lines of best fit, or linear equations? Can we use those same ideas to fit this nonlinear equation to this data? And I claim yes, and here's how we're going to do it. All we need to do is take this model equation, which doesn't look linear, and match it up somehow to an equation of the form y equals mx plus b. So the job is we just want to make the thing on the left look like the thing on the right. All we need to do is to identify what's playing the role of each of these four variables and parameters over here in this equation, the y, the m, the x, and the b. So first of all, in both of these equations we have a subject. Both of these equations have been solved for one particular variable. So it probably makes the most sense to treat h as our dependent variable. So in other words, I'm going to graph these data points where on the vertical axis I'm going to place values of h. What's the next thing that we can identify pretty straightforwardly? Well, we have in both of these equations a term that is just a constant parameter by itself, sitting out in the front. Right? We have a b, the vertical intercept of the linear equation, matches up with this h naught, which is the initial height of the object that we dropped in the model equation that we're working with. So when we find a linearized equation for this, the vertical intercept is going to match up with that initial height, h naught. So this is playing the role of our b, and then we said h was playing the role of y. So now that just leaves the m and the x. So first of all, whatever we identify x with had better be an expression which is related to our independent variable. So looking in this product of conglomeration of factors over here, minus g over 2 times t squared, which portion of that factor is constant and which portion of that factor is variable? Which portion of minus g over 2 t squared is constant? The minus g over 2 piece. That piece is constant, and therefore, because that's a parameter in our equation, we're going to match that up. Whoops. We're going to match that parameter up with our slope. And that just leaves the variable factor, the t squared, as what we're going to match up with our x. So this is the degree of difficulty in linearizing an equation, is we have to just go through and identify what are we thinking of as being our y, what are we thinking of as being m, what are we thinking of as being x, what are we thinking of as being b. And we have a lot of freedom in which to do that. But what it means at the end of the day is that if I want to see this data as linear instead of nonlinear, then I don't want to treat t and h as my independent and dependent variables. Instead, I want to treat t squared and h as my independent and dependent variables. Does that make sense? So what I want to do is, instead of plotting the values of t, which in this example were 1, 1.5, and 2.5, instead of plotting values of t, I want to plot values of t squared. And in this app, I can do that just by clicking a button in a moment. So let's, again, plot on the horizontal axis. Instead of plotting our values of t, let's plot our values of t squared. So I'm just going to choose the axis transformation x squared down here at the bottom and redisplay. And once I've done that, notice what just happened. The data points that we had placed on our original graph remain the same. But on our transformed graph, the graph we're looking at on the right now, what just happened? The graph linearized. because now we're plotting t squared versus h. Now we should be able to tell whether or not this fits the model equation that we started with. Remember, that was h equals minus g over 2 t squared plus h naught. And again, what we have on the right-hand side now is a graph which looks a whole lot more linear. I mean, we were doing pretty well with our correlation coefficient before, but look at how good it is now. R squared equals 0.999793. So we have something that looks linear. Let's just call it what it is. It's linear over on the right-hand side. So our transformed graph is linear. And on the left-hand side, what you're seeing is an equation, a nonlinear equation now, which fits our nonlinear data. That parabola that we were looking for is now looking at us in the face. So the upshot of this is that as soon as we know how to fit a line to a set of data, we're also going to be able to use that same technique to fit curves to data. As soon as we have a model equation, like the equation we have down here. Now the portion that I'd like for you to do is to, with your groups, figure out, based on the information that's on this screen. So we have here the result of our line of best fit over here at the upper right, and our correlation coefficient. And I'd like for you to figure out what this all means. Specifically, how can we use this data that's on the screen right here to tell me what do the slope and intercept of this line mean? And then second of all, to tell me what was the initial height from which this object was dropped on the moon, and what is the acceleration due to gravity on the moon, according to the information that you see here. So our first exercise for the day, get into your groups and see if you can come up with an answer to these questions based on the information that's up here on the screen.